Okay, so we're ready at this point to kind of bring it all together. Section 3.2 is going to tie things together, and we're finally using a different example. Yay! And what we're going to do is put our process all together. And the process, if you remember, we want to be able to find the general solution for this, and we're going to do it by hand. We could, if we wanted to, turn it into a system of differential equations and have Maple do it. So we can always check it with Maple. But our process for this has a couple of steps. The first step is going to be we got to find those eigenvalues. And once we have the eigenvalues, we can find the associated eigenvectors. And once you have eigenvalues and eigenvectors, you can write the two, because there's going to be two, both straight line solutions. And then the very last step is write the general solution. And we're going to put that together from our straight line solutions. So really, we've got 4 steps, and the first 2 are where most of the work on this process happens. And sadly, those are the 2 easy ones that Maple can do for us really quickly. So if you wanted to do this fast, it's really easy to do in Maple. So let's do this by hand, doing it by hand, step by step. So step 1 is going to be finding those eigenvalues. And so I'm going to try to color code some things here. And remember, the eigenvalues, it's all about that coefficient matrix, but we're going to find the determinant of the modified coefficient matrix. Remember, 2 and 3 are going to have minus lambda attached to them. So 2 minus lambda, 2, 1, 3 minus lambda. And we're looking for where the determinant of that thing is equal to 0. And if you recognize this, you're like, oh, determinant is just multiply diagonal, subtract the other diagonal multiplied. And so this is going to be 2 minus lambda quantity times the quantity 3 minus lambda minus 1 times 2. And so I'm going to shift this over to the side so that we have a little bit more space, because this is really just the, when we multiply this out, this is going to be a quadratic. There we go. And it's going to be lambda squared, that last term, lambda squared. The middle term is going to be minus 3 lambda, minus 2 lambda, so minus 5 lambda. And then the last term is going to be plus 6. And then we have minus 2. Can't forget about that term right there. And so a little bit of simplification. We have lambda squared minus 5 lambda plus 4 equals 0. And this is a quadratic equation that we can totally solve. And in this one, it just happens to be factorable, which makes it nice and easy for us. And that factors nicely as lambda minus 1 times lambda minus 4. So there's 2 eigenvalues. And so I'm going to call this one number 1. I'll call that lambda 1 equals 1. And I'm going to call this one lambda 2 equals 4. So there's 2 eigenvalues. We just found the eigenvalues. So step 1 is done. Step 2, now that we know the eigenvalues, we can find their associated eigenvectors. So step 2 is all about what are the eigenvectors. And eigenvectors require us to kind of take each one of these one at a time and use that familiar equation of A times the eigenvector must be equal to lambda times the eigenvector. So we're going to do this for each one of our eigenvalues in turn. So for lambda 1 equals 1, we're going to use our equation, our handy-dandy equation. And this is super important, so I'm going to write it down up here just as a reminder that this thing must be true. A, the coefficient matrix, times the eigenvector v has to be equal to lambda times the eigenvector v, right? So for each one of our eigenvalues, that has to be true. So for lambda 1, we can say 2, 2, 1, 3, that's our A coefficient matrix, times some eigenvector. And we can write it as v1. The problem is I want it to be in terms of some x and y value. I'm going to call this x1 and y1. And you'll see why in a minute, because we're going to do this for lambda 2 over here, and they're going to be different eigenvectors. So that's got to be equal to lambda 1, which in this case is going to be 1 times x1, y1. And I don't know, personally I like just turning this into a system of equations and rewriting this as the system of equations 2x plus 2y, and those are both with little subscript 1, is equal to x1 on the top, and on the bottom it's going to be 1x1, so x1 plus 3y1 equals y1. Now remember what we did before. We kept them as a unit, as a pair of equations, and we manipulated them. And so this is the equivalent of, if I manipulate this guy, I'm going to get my x's all on the same side and then solve it for y equals. And when I do that, I'm going to move my x's to the same side, and I have 2y1 equals negative x1. And on the bottom equation, I have, get my y's together, I'll have x1 equals negative 2y1. Now you might think those are different equations, but when they simplify, you actually get the exact same thing. Both of them say the same thing, and they both say y1 equals negative 1/2 x1. Right? And what is that really telling me? That's telling me the direction of my vector. That's telling me the direction of eigenvector 1. So I can look at them and say, so that means eigenvector 1 must be equal to, whenever x is 1, y would turn out to be negative 1/2. And it turns out that that is a perfectly acceptable form for this as an eigenvector. But if you're not a big fan of fractions, you could instead say when y is equal to 1, then x would have to be equal to negative 2. This is equivalent to, another form of this eigenvector is negative 2, 1. They're both the same. They both actually mean the same thing because they're both pointed in the same direction. Right? They're both pointed along the same line. And either one of them is acceptable. If you like this one because it's simpler to get, that's fine. If you like this one because it doesn't have fractions, that's fine too. So whichever way you go, you've got your v1. And if we did the same thing for lambda 2, the setup is going to look very similar. We've got our coefficient matrix. But this time it's times not x1 and y1, it's x2 and y2. And I'm just using the subscript to identify the fact that this is going to be associated with my eigenvalue number 2. And so that's got to be associated with lambda 2 is equal to 4. So this is going to be 4 times x2, y2. So this system of equations that we get from here is a little bit different. Well, not on the left side, it's not. It's going to be 2x2 plus 2y2. And the right-hand side is 4x2. And the second equation is x2 plus 3y2 equals 4y2. And again, we're going to manipulate this system of equations until they tell us either the same thing or they tell us something like 0 equals 0, which is kind of duh. In this case, they're going to tell us the same thing. And we're going to have a system of equations. And on the top, if we get our x's and y's together, we'd have 2y2 equals 2x2. And in the bottom, we'll have, move the y2 to the other side, and we just have x2 equals y2. So both of them are telling us the same thing. Both say y2 equals x2. So we know the eigenvector associated with that eigenvalue is really just whatever x is, y is. So if x goes up by 1, y goes up by 1. There's my eigenvalues, and now I have my eigenvectors, whichever one you want to use here. It doesn't matter. So number 3 in the process, if you remember from up here, was write down both of our straight line solutions. So let's do that. We're going to write the straight line solutions. And so we have two of them. One of them, I'm going to use color coding on this one. So I'll use straight line solution number 1, and that's going to be associated with lambda 1 equals 1 and v1 equals, I'm going to use this one, just to make it more interesting. -2, 1, just for fun. And so writing the straight line solution, if you remember, all straight line solutions are of the form y equals, and so this is going to be y1 of t equals, there's no constant in front of it, it's just e to the power lambda times t, so e to the 1t, whoops, let me scooch it up, times my eigenvector that's associated, so -2, 1. Now you'll look at this, remember this is a matrix equation because there's technically two equations buried inside it. There's the x of t equation, which is this times -2, and then there's the y of t equation, which is the bottom one. Right? So that's y1, and I can do the same thing for the straight line solution number 2. And that's the one that's associated with lambda equals 4 and v2 equals 1, 1. And so its straight line solution, again, is going to be following the same pattern, but it's now going to be e to the 4t times the eigenvector 1, 1. And again, that's two equations tucked in there. And so we're almost done, and I'm just going to go into the next page because I don't want to squeeze it in on the bottom here. There's not a lot of space. But step 4 is to take those two straight line solutions and combine them into the general solution. So on the bottom of, this page, or the top of the next page, I'm going to kind of scoot this up so I can do my next step, my last step, which is step number 4, write the general solution. And so the general solution is a combination of those straight line solutions. You can think of it as big Y of t is what you get when you stick a constant in front of y1 plus a constant, a different constant, in front of y2, your two straight line solutions. Right? Oh, sorry, number 2. And so that's what we're going to do. So let me scoot this up, because I'm going to write down underneath, our general solution is going to be of the form y of t equals some constant, which we don't know, times my y1, which is this guy right here, times e to the t, times its vector, -2, 1, plus another constant, times e to the 4t, times its eigenvector, and we are done. That is the general solution for this coefficient matrix, or for that system of differential equations. So what we have found is the matrix form, or sometimes it's referred to as the vector form of the solution. But we could, if we wanted to, rewrite that in scalar or parametric form. And the scalar or parametric form, just remember, this is the same thing as an x of t and a y of t. So you've really got a pair of equations that look like this. The x of t is going to be the top, and so that's going to be k1 times e to the t times -2. So I'm going to stick the negative in front of that, times, oops, I'm just going to put -2 right there. Don't be cute. Just do what you're told. Times -2 plus k2 e to the 4t times 1. That's my x of t. My y of t is just going to be the bottom part of this. And so that's going to be k1 e to the t times 1 plus k2 e to the 4t times 1. And so what we've done here is we've found the parametric form, or you can think of it as the scalar form. Now, pretty easily you can say, well, the scalar form makes more sense to me because it's x coordinate and y coordinate. I can see what happens to x. I can see what happens to y. Notice, as time goes by, we expect t to get bigger and bigger. That means these two are going to get larger and larger. Depending on what the constants are, they're either larger negative or larger positive. But we expect y to kind of blow up in size. Same thing happens here with x. We expect x to kind of blow up in size. But it turns out that the way we've written it up here in matrix form allows us to see how it's behaving exponentially coupled with what direction that straight line solution is going. So we expect to see from this, we expect two straight line solutions. One is going to be along the line, and this is just from the previous page, y equals negative 1/2 x, and then the other is going to be along the line y equals x. And these are our kind of the directions that we got from finding our eigenvectors. And sure enough, when you look at the phase plane for this, this is me generating the phase plane for this, you have one that looks like it's along the line y equals x. And so that would be our straight line solution number 2. And then the other one looks like it's along this path right here, which is our straight line solution number 1. That's along the line y equals negative 1/2 x. And the cool thing is, every other solution curve, whether I start here and draw a solution curve that looks like this, or whether I start over here and I draw a solution curve that looks like that, or whether I draw a solution curve that looks like this, or like this, every single solution curve on this phase plane is really just a combination of these two straight line solutions. That's because my general solution really is just a combination of these two straight line solutions, some multiple combination of those straight line solutions. So this is huge. What we've just found is enormous. We've discovered that any particular solution on the phase plane is a linear combination, that's the fancy way of saying it, of the two straight line solutions. And so that means if you can find the straight line solution, you can find any particular solution. And our two straight line solutions that are clearly evident right there, we can go back to our old color coding and say that this straight line solution right here, oops, wow, man, I got the wedge wrong. That guy right there, that's the straight line solution y1. And this guy over here, see if I can draw this one better. Sort of a straight line, if I could draw in a straight line. That's my y2. Now we're going to learn more about what's going on with our straight line solutions and how we can interpret them throughout the rest of this chapter. But we now have the ability to find the general solution by coming up with the straight line solutions by finding the eigenvalues and the associated eigenvectors for our system. So that's pretty cool. And that gets us to the end of section 3.2.